Hi everyone. I am Sanal Kumar A P, a research scholar in School of Chemical and Biotechnology, SASTRA Deemed University. Here I present a brief overview of my PhD thesis entitled Performance Enhancement and Modeling of Thermochemical Conversion of Herbaceous and Hardwood Biomass via Co-Gasification with Integrated Sustainability Evaluation. In this presentation, I will highlight the research motivation, methodology, key findings, and major contributions of my work toward the sustainable utilization of agricultural residues and woody biomass for clean energy production. Here I work under Dr. V. Ponnusami, Associate Dean, School of Chemical and Biotechnology, SASTRA Deemed University. Agricultural residues such as rice husk, sesame stalk residue are abundantly available on, but are often burned in open fields, leading to severe air pollution and underutilization of valuable biomass resources. Similarly, Prosopis juliflora, an invasive woody biomass, possesses environmental challenges despite its high energy potential. Although several studies have investigated biomass gasification, most have focused on individual feedstock or only experimental investigations with limited integration of process modeling and sustainability assessment. Therefore, this research aimed to develop a comprehensive framework by characterizing the selected biomass feedstock, enhancing gasification performance through pelletization and co-gasification, developing and validating an Aspen Plus model, and evaluating the thermodynamic and environmental sustainability of the process using exergy analysis and life cycle assessment. The study began with a comprehensive characterization of the selected biomass feedstock through proximate, ultimate, heating value, thermogrammetric, and kinetic analysis. Experimental investigations were then carried out in a 5 HP throttless downdraft gasifier operating in batch mode using air as a gasifying agent. Both individual biomass gasification and co-gasification of herbaceous biomass blends with hardwood Prosopis juliflora were performed to evaluate gasification performance based on the experimental data. An Aspen Plus gasification model was developed and successfully validated against the experimental results before being used to optimize operating conditions. Finally, exergy analysis and life cycle assessment were conducted to evaluate the thermodynamic and environmental sustainability of the developed gasification system. From the experiments, we concluded that from the kinetic analysis, we concluded activation energy for all the three biomasses ranged from 147 to 480 kilojoule per mole, kilojoule per mole, where SR showed the higher activation energy and PJ exhibited more favorable decomposition characteristics. From the gasification performance, we identified that the blend of S1 R1 P2 in 1:1:2 ratio performed well with cold gas efficiency of 46.2 percentage, and after pelletization it is improved to 69.77 percentage. In modeling and optimization, model agreement was obtained with an RMSD value of 0.99, and the PJ rich and RH moderate blends performed best, especially under steam conditions, where we obtained cold gas efficiency up to 65 percentage. When we come to exergy study, PJ exhibited the maximum value of 43.03 percentage in air gasification, while in steam gasification it performed 52.80 percentage. Also, the blend ratio with the S1R1P2, the same 1:1:2 blend ratio, showed the maximum exergy efficiency for 27.76 with the air and 32.54 with the steam. When coming into LCA study, PJ showed the lowest GWP value, and S1R1P2, the same blend ratio, showed the best as a best blend ratio. When we compare to the coal-based system, it was a highly very high values of carbon equivalent was there when we compared with the 1000 kilowatt hour of energy production. And there was 62% reduction in GWP compared to coal-based system, and diverting residues from open field burning to gasification provides additional GHG emission reductions. And finally, we concluded that PJ and PJ rich blends deliver higher syngas quality, better energy efficiency, and a lower environmental impact. And the blend ratio, we confirmed that 1:1:2 emerged as the most sustainable biomass blend, balancing with a balancing performance, thermodynamic, and environmental benefits. In conclusion, I thank Shastra Deemed University and all our lab members. This work carried out at ASK2 room 316 Bioprocessing Intensification Laboratory, School of Chemical and Biotechnology. The research resulted in two publications in the international journal Renewable Energy, published by Elsevier. I sincerely acknowledge the financial support from DST, City Union Bank, CSR, NSRF, and all other funding agencies. In conclusion, the research demonstrates an integrated framework for efficient biomass gasification using agricultural residues and woody biomass for clean and decentralized renewable energy production. And thank you for your kind attention.